Today we'll be starting on the final chapter of Unit 5, which is Organic Chemistry. This is Study Pack 18. I hope you have got the hard copy of this. This is a chemistry of aromatic compounds. In fact, in A2, the main study on Unit 5, Organic Chemistry, the main study will be the study on the aromatic compounds. The Unit 4 we studied, Unit 4 as well as the AS we studied the aliphatic compounds. Aliphatic compounds are the long chain molecules like alkanes, alkenes. They are referred to as aliphatic hydrocarbons. And as you know, hydrocarbons are compounds which contains only carbon and hydrogen. And hydrocarbons are of three types: aliphatic, alicyclic, and aromatic. So aliphatic meaning they are straight chain ones like alkanes, alkenes, they are aliphatic. Alicyclic hydrocarbons, they are cyclic hydrocarbons, right? For example, cyclohexane, cyclopentane, cyclohydrocarbons, cycloalkanes and cycloalkenes, they are recyclic. The aromatic ones, they are also cyclic, but there is a delocalized pi ring of electrons in the center. For example, if you take alicyclic cyclohexane, this is cyclohexane. Aromatic will be cyclic, but there is a ring of pi electrons in the middle. Shortly, I'll be explaining what is this ring and how this ring is formed, right? So this in Unit 5, the chemistry will be the study of the organic chemistry will be the study of the aromatic compounds and derivatives of the benzene and benzene derivatives. Benzene is the aromatic compound, which the formula of benzene is C6H6. You have 6 carbons and 6 hydrogens in a molecule of benzene. In fact, there was a lot of research was done at the initial stages about benzene. Scientists couldn't figure out the structure of benzene, right? Because you can't draw a linear structure with 6 carbons and 6 hydrogens. You will not be able to fill the valence electrons of carbon and hydrogen, especially the carbon. So there was a question mark for a long period of time as for the structure of benzene. What can it be? What is this C6H6 structure is? Up to the point, there are so many scientists involved that Auguste Cacoule, sometimes his name is pronounced as Auguste Cacoule or Cacoule. Up until he saw a dream one day, he saw a snake biting its own tail. He saw a dream of a snake biting its own tail. Then he realized the benzene molecule, which is C6H6, has to be a cyclic one, right? Because they found from the percentage composition analysis that one benzene molecule will have 6 carbon atoms and 6 hydrogen atoms, right? So, but the structure was unknown for a long period of time up until Cacoule saw this dream, snake biting its own tail, right? So then he realized the benzene has to be a cyclic one. So he proposed the benzene structure this way: 6 carbons are in a cyclic form like this, where each carbon atom is linked to a hydrogen. Cyclic carbon like this. Carbon chain is cyclic, so 6 carbons, and each carbon atom is linked to or covalently bonded to the hydrogen, right? And there are now the carbon should have 4 bonds, right? No 4 bonds for carbon. Each carbon only has 3 bonds. So what he did was he put these double bonds, alternate double bonds in carbons. That means alternate carbon has a double bond. So now if you analyze its structure, this structure has all carbons, 6 carbons and 6 hydrogens, and all the carbon atoms have 4 bonds. Valence is 4. The skeletal form, you can represent this structure as this way. It doesn't matter where you put the double bond. You can even put the double bond here, but it has to be alternate. If you put the double bond here, the next carbon will not have a double bond. If I have a double bond here, if I put a double bond here, that carbon will have 5 bonds. So alternate double bond. Doesn't matter where you begin and where you end, right? So this was a structure which was proposed by Auguste Cacoule. So there are a lot of scientists involved at that time about studying about the structure, but not everyone was happy with this structure. There are various reasons why they didn't accept this structure of Auger's calculus, right? One of the main reasons they said was that if benzene contains double bonds like shown in the structure, the first thing it should do is that it should decolorize bromine. We know any molecule which has carbon-carbon double bond should decolorize bromine, right? But benzene doesn't decolorize bromine. So first question mark on the Auger's calculus structure is that if this structure is true, when bromine is added, it should decolorize, but the bromine doesn't decolorize. Second, during hydrogenation of a carbon-carbon double bond, that is adding hydrogen to alkene, if you hydrogenate one carbon-carbon double bond, it releases minus 120 kilojoules per mole energy. It's exothermic process. Hydrogenation is exothermic process. So when you add hydrogen to ethene, it releases 120, right? This is one carbon-carbon double bond. But therefore, as to the Auger's calculus structure, benzene has 3 double bonds. So therefore, they said if it has 3 double bonds, during hydrogenation of benzene, it should release 3 times of 120, which is 360, right? 360. But in reality, benzene only releases minus 208, much less than the 360. Second question mark on the Auger's calculus structure, right? Then they said also that if if it contains double bonds and single bonds alternatively, it has to be not a regular hexagon. They found from the later on they found from the X-rays, once X-rays invented, then they found that benzene is a perfect hexagon. But we know the double bonds are shorter, single bonds are longer. So in fact, benzene has to be like this, right? It can't be a perfect regular hexagon this way, right? So third question mark. And also the bond lengths, all the bond lengths of, now if you take a carbon-carbon single bond, is carbon-carbon single bond in ethane, it's 0.154 nanometers. This is for ethane. And the carbon-carbon double bond in ethene is 0.134. See, double bond is shorter than single bond. But the benzene is a regular hexagon. The carbon-carbon bond is neither these two, it's in between value. So that's another question mark. How can this have double bonds? So these all were the reasons why at the initial stages, Auger's calculus approach was not successful. Not everyone was happy with it, even though he produced an answer to a problem where no one knew what it is. But Auger's calculus structure, even though it is not correct, but this is very close to the true structure. True structure will be explained shortly, right? True structure of benzene will be done shortly, based on the orbital hybridization concept, because at that time, at Kaku's time, the concept of orbital hybridization was not developed, so he couldn't explain in that way. But he did, I would say, about 90% of the work of identifying the structure of benzene, right? So the formula of benzene is C6H6, which can be experimentally shown by the percentage composition by mass. Kakule proposed the structure of which carbon atoms in benzene forms a regular hexagon with each carbon atom sigma bond and the other alternately with the pi bond. Please copy the displayed formula and the skeletal formula of benzene. Okay, there's a question, explain the perfect hexagon. In fact, X-ray diffraction of the benzene structure shows that benzene is a perfect hexagon. But as the benzene, there are double bonds and single bonds, right? So double bond is shorter. Double bond is shorter, but single bond is longer than the double bond, right? So therefore, it cannot be a regular hexagon. And so it will be irregular hexagon in that case, because double bond is shorter, single bond is long. Double bond is short, single bond is long. So it has to be something like this then, right? So it can't be a regular hexagon. So benzene molecule has a regular hexagonal shape and is planar. This is proven by X-ray diffraction, but the calculus structure would not be a regular hexagon, as a carbon-carbon single and double bond lengths are not equal. The bond length of benzene is 0.134 nanometers, which is roughly the halfway of the carbon-carbon single and double bonds. Calculus structure is unsaturated, therefore benzene should undergo addition reactions as ethene, but this is not the case. Instead, it undergoes substitution reaction, which means the benzene does not decolorize bromine. When a carbon-carbon double bond is hydrogenated, it releases minus 120 kilojoules per mole energy. As benzene contains 3 carbon-carbon double bonds, as per the calculus structure, it should release 360, but in reality, benzene releases only 208. And also, you can compare the IR spectra. The carbon-carbon double bonds and single bonds wave numbers will not match with the wave number of the carbon-carbon bond in benzene. And if calculus structure is correct, that means there'll be 4 isomers for dibromobenzene. Now, for example, if I take dibromobenzene, now see, dibromobenzene, you can draw this isomer. You can have this isomer, and you can have this isomer. 1,2-dibromobenzene, 1,3-dibromobenzene, and 1,4-dibromobenzene, right? So if calculus structure is correct. But the thing is, we are only 3 isomers for, it's actually 4 isomers. I only drawn 3. Fourth one will be this. 1, 2 I have drawn, 1, 3 I have drawn, 1, 4 I have drawn. I can draw another isomer like this, which is 1, 2, but you can notice here the 2 carbons, these 2 bromines are across the carbon-carbon double bond. This is not across the carbon-carbon. So the thing is, as to the calculus structure, there should be 4 isomers. But in practical, we'll be discussing later, it is only 3 isomers. So that's also proof that the calculus structure is not correct. Please copy these 4 isomers of dibromobenzene. Right, so let's see how calculate tried to overcome these problems. It had to manage to, I think, most of the problems he overcame with, not all, but he said these carbon-carbon bond, double bonds, they are not in one place. He said they rotate, meaning this double bond comes here, this goes there, and this comes there. So this will give rise to this structure, like this. And likewise, these double bonds again keep rotating and give rise to the other structure. Right, so you can use this double-headed arrows here. Double-headed arrows represents the resonance structures. Resonance structures meaning canonical structures. They are the same structure but different orientation. They are not isomers, but they are different orientations. Benzene can exist this way or the other way. So what did Kakule said? That he said a carbon-carbon bond in benzene is neither a single bond or a double bond. It's something in between, because These bonds in benzene keep changing. They keep changing. So they are something in between. So, or in other words, they exist as resonance structures, or he said they exist as canonicals. Canonicals is another name for resonance structures. So he managed to overcome a few of the problems, but still, like decolorizing bromine, still there's double bond somewhere, right? That problem is a question mark. And also the regular hexagon matter was solved. So they agreed, because it's not a double bond or single bond. From the bond energies, we know something in between. It's the bond energy of the benzene, carbon-carbon bond is between the double bond energy and the single bond. So from that he derived that it is something in between double and a single bond. So he said these pi bonds keep rotating, keep changing. So that was very helpful for the development of the modern orbital concept, or the modern orbital theory of benzene, right? Yeah. So Kakulu suggested that the proposed structure of benzene exists as resonance structures. The double-headed arrow is to represent the resonance structure, which means that the actual structure lies between the two representations. Therefore, each carbon-carbon bond is neither a single nor a double bond, but an intermediate type. The 3 pi bonds are delocalized, meaning shared between the carbon atoms. This concept overcomes the difficulties of the shape and the bond length of the benzene molecule. That means it will be a regular hexagon, and the bond length is between the carbon-carbon double bond and the single bond. But still, he couldn't answer why benzene does not decolorize bromine, right? Please copy the canonical structures. So let's look into the modern orbital theory of benzene. What is the actual structure of benzene, and then how it is derived. In fact, the actual structure of benzene is explained using the concept of orbital hybridization. If you remember, we discussed about the hybrid orbitals in AS. Hybrid orbitals are mixed orbitals. For example, if you take methane, right, methane, the carbon-hydrogen bonds in methane are exactly the same. It has same bond lengths and same bond energy. CH bond lengths are same, and energy also will be the same. But if you analyze carbon, the carbon forms bonds with hydrogen with 2 different orbitals. You can see the electronic configuration: 1s2, 2s2, 2p2. So the outermost shell, which is a valence shell of carbon, has the configuration like this, as to the Hund's rule. This state is known as the ground state. I hope you remember your A's. The ground state is the state before forming any bonds. The element is in ground state. But as to the ground state, you can see carbon only has, or it possesses only 2 unpaired electrons, which means carbon can only form 2 bonds with 2 hydrogens like this, sharing the 2 electrons. But that's not the case. Carbon forms 4 bonds, right? So atoms form bonds in the excited state. That is, the electron from the S2 get excited to a high level. This is known as the excited state. So atoms form bonds in the excited state. Now, how this promotion occurs? It requires energy for this promotion. It won't just go to a high level. You have to give a certain amount of energy. And that energy is given by the bond formation process, right? Because we know to break a bond, you have to supply energy.